Hello friend, welcome to the abstract algebra class. It is class 74. In this class we will prove some example by using Cayley's theorem. In the last lesson we proved the Cayley's theorem, which is every finite group is isomorphic to a permutation group. Here that kind of permutation group is called regular permutation. Now we want to solve a problem. Find the regular permutation group isomorphic to the multiplicative group G is equal to 1 the omega square. This group is abelian and under multiplication, so we can say that multiplicative group. This group G we call multiplicative group because this is abelian group. Under multiplication, therefore we can say multiplicative group. Solve, given that G is equal to 1 omega square be the multiplicative group. By Cayley's theorem we define a mapping FA such that G into G defined by FA of x is equal to AX for all x belongs to G. Now we want to find the permutation group. Now if one is equal to 1 omega square 1 omega square. How we can find this? According to the definition, we use this formula and find if one of w, this is the value of f1 of w, we omega. If 1 of 1 is equal to 1 into 1 is equal to 1. If 1 of omega is equal to 1, here 1 is A and here omega is X. A into X, 1 into W is equal to W. If 1 of omega square is equal to 1 into omega square is equal to omega square. If you want to count if omega of 1, here omega is A, 1 is X. Therefore we can write it is equal to omega into 1 is equal to omega. If omega of omega is equal to omega into omega, it is X. A into X, according to the definition. A into X, omega into omega square. If omega of omega square is equal to omega into omega square is equal to omega cubic is equal to 1. Therefore we find w if w of 1 is equal to omega, if omega of omega is equal to omega square, or if omega of omega square is equal to 1. Similarly, we can find if omega square is equal to 1 omega square. If omega square of A1 is omega square. If omega square of omega is 1, if omega square of omega square is omega. Now the regular permutation group corresponding to G is G dash is equal to F1 if omega square here. Therefore, by Cayley's theorem, G is isomorphic to G. Here is another problem. Find the regular permutation group isomorphic to the multiplicative group. Group G is equal to 1 minus 1 I minus I. We know that this group is abelian group. Here the binary operation is multiplication, therefore G is multiplicative group. So, we want to solve this problem. Given that G is equal to 1 minus 1 I minus I be the multiplicative group, multiplicative group by Cayley's theorem. Define define a mapping fa of x is equal to a mapping fa such that g into g dash by fa of x is equal to a into x for all x belongs to G. Now we want to find the permutation group F1. Here we have 4 elements, so F1 is equal to 1 minus 1 I minus I. F of 1, if we want to find f of 1, f1 of 1 is equal to, according to the definition, 1 into 1 is equal to 1. Therefore, if you find f1 of minus 1 is equal to 1 into minus 1 is equal to minus 1. Therefore, f1 of minus 1 is equal to minus 1. Similarly, I minus I. If f minus 1 of f minus 1 is equal to 1 minus 1 I minus I. If you want to find f minus 1 of 1 is equal to minus 1 into 1 is equal to minus 1. Minus 1. F minus 1 of minus 1 is equal to minus 1 into minus 1 is equal to 1. 1. F minus 1 is equal to of I is equal to minus 1 into I is equal to minus I. Minus I. F minus 1 of minus I is equal to minus 1 into minus I is equal to I. If I is equal to 1 minus 1 I minus I. It is I into minus I into I minus 1 I minus into minus I, it is 1. F minus I is equal to 1 minus 1 I minus I. It is minus I into minus 1 I minus I into minus I into I. It is 1 minus I into minus I minus 1. Now the permutation group corresponding to G is G dash is equal to F1, F minus 1, Fi, F minus I. Therefore, by Cayley's theorem, G dash is isomorphic to G. Here is multiplication is the binary operation. F1, F minus 1, Fi, F minus I. f1, f minus 1, fi, f minus I. f1 of f1 it is identity permutation. f1, f minus 1, fi, f minus I, f others f1, f minus 1, fi, f minus I. Now f minus 1 into f minus 1, actually f minus 1 into f minus 1 is equal to 1 minus 1 I f minus 1 into f minus 1 is equal to 1 minus 1 I minus I minus 1 minus I into 1 minus 1 I minus I minus 1 minus I. It is equal to 1 minus 1 I minus I. Here the image of minus 1 is minus 1. 1 is minus 1. The image of minus 1 is 1. The image of minus 1 is 1. The image of 1 is minus 1. The image of I is minus I. The image of I. The image of minus I is I. I is minus I. It is equal to f1. Similarly, we can find others. It is your work to complete this table. Problem. Now we want to solve a problem. Let Sn be a symmetric group. Symmetric, nothing but permutation group. On n samples An be the group of even permutation. We have to prove that An be the normal subgroup of Sn and order of An is equal to n factorial by 2. Solution. We know that the set of G is equal to 1 minus 1. We know it is an abelian group under multiplication is an abelian group with under multiplication or with respect to multiplication. Define an a mapping the phi size that Sn into G by phi of f is equal to 1 if f is even permutation, minus 1 if f is odd permutation. For all f belongs to Sn. Let f comma g belongs to Sn. Then there is three condition. 1, f comma g both are even permutation. Then f of f is equal to 1. F of g is also equal to 1 according to that definition. Number 2, f of f comma g both are odd permutation. Then we get f of f is equal to minus 1 and f of g is also minus 1. Third one, f is even and g is odd permutation. Then f of f is equal to 1, f is even, and f of g is equal to minus 1 because g is odd permutation or g is even. Then f of phi of g is equal to 1 and f is odd permutation. Phi of f is equal to minus 1 because f is odd permutation according to the definition of function phi. Now we want to show that this condition satisfies definition of homomorphism. Number 1, f comma g both are even permutation. This implies f into g is also even permutation. We know that the multiplication of two even permutation is even. This implies f of f into g, phi of f into g is equal to 1 because f into g is even permutation. So according to the definition, we can write phi of f into g is equal to 1. We can write 1 into 1. Phi of f and g both of are even. Therefore, instead 1 we can write phi of f. Instead 1 we can write phi of g. Number 2, f comma g both are odd permutation. Then the product of two odd permutation is even permutation. Therefore, phi of f into g is equal to 1. It is equal to minus 1 into minus 1. It is equal to phi of f into phi of g. Instead minus 1 we can write phi of f because f is odd permutation. Instead minus 1 also we can write phi of g because g is even odd permutation. If f is even and g is odd permutation, then f into g is odd permutation. The product of an even and odd permutation is even and odd permutation. This implies phi of f into g is equal to minus 1. Here, odd permutation, phi of f is odd, then phi of f is equal to minus 1. F into g is odd permutation, phi of f into g is equal to minus 1. We can write 1 into minus 1. Instead of f is even permutation, we can write, instead 1 we can write phi of f, instead minus 1 we can write phi of g. Hence, phi of f into g is equal to phi of f into phi of g. For all f comma g belongs to Sn. Therefore, phi of phi such that Sn into g is homomorphism. In 3 cases, we verify that phi satisfies the definition of homomorphism. Also, by definition, phi is onto. Because phi is onto, because for every element from Q domain there is an element in domain. Now by fundamental theorem of homomorphism of group, we know that Sn by kernel f is isomorphic to G. It is relation 1. Here kernel f is equal to f belongs to G. Kernel f is equal to f belongs to G such that phi of f is equal to 1. It is equal to phi of f belongs to G such that f is even permutation. It is equal to An, which is group of even permutation. We know that kernel f is a normal subgroup of Sn. That is, An is a normal subgroup of Sn. Kernel is equal to An. Kernel is normal subgroup. Therefore, An is also normal subgroup. Since Sn by An is equal to G, this implies order of Sn by An is equal to order of G. This implies order of Sn into by order of An is equal to order of G. This implies order of Sn is n factorial, order of An is equal to order of G. G has 2 elements. Therefore, order of G is equal to 2. This implies order of An is equal to n factorial by 2. We should remember there some basic information to prove this problem. Sn is isomorphic to Sn is a permutation group. Sn is a permutation group which is its order is n factorial. An is an alternative group or A1. Here is A1 group, A1 permutation. Its order is n factorial by 2. Also we know the product of A1 in permutation into A1 permutation is A1. A1 permutation, odd permutation into odd permutation, it is A1. A1 permutation into odd permutation, it is odd permutation. They are the basic information to prove to solve this question. Thank you.